Welcome to Spaceverse, your portal to cosmic adventures. The supermassive black hole at the center of the galaxy M87 holds a very special place in astronomy. It's the first black hole humanity ever managed to photograph. That iconic image, released in 2019, showed a glowing orange ring surrounding a dark shadow, a cosmic portrait that marked a historic milestone for science. But as groundbreaking as that image was, it was only the beginning. Now, the James Webb Space Telescope, with its extraordinary infrared capabilities, has taken us even deeper into the heart of this galactic monster. And what it found reveals a story more dynamic, more mysterious, and more breathtaking than ever before. For more than a century, astronomers have marveled at the incredible jet of matter blasting from the heart of M87, a massive elliptical galaxy located about 55 million light-years from Earth. This jet isn't just a streak of light. It's a colossal, high-energy beam of charged particles that shoots out thousands of light-years into space. It's so powerful that it can outshine entire galaxies, and it's fueled by the gravitational fury of M87's central supermassive black hole, known as M87. Now, thanks to the James Webb Space Telescope, or JWST, we have the clearest-ever infrared view of this cosmic powerhouse. And in that stunning new image, Webb has captured something scientists have been chasing for decades. The faint, ghostly glow of the black hole's elusive counterjet, a second stream of matter firing off in the opposite direction, almost hidden from view because it's moving away from us at nearly the speed of light. In Webb's breathtaking new image, the main jet appears as a brilliant pink ribbon unfurling across a soft violet background, like an interstellar streamer dancing through the void. The stream of charged particles extends several thousand light-years from the galaxy's central black hole, with glowing nuts scattered along its length. Each nut marks a region where particles are being violently accelerated to near light speeds, a process so extreme it defies the limits of physics as we know them. And then, about 6,000 light-years away from the black hole, lies something faint and delicate, the counterjet. It's dim, almost ghost-like, but unmistakable. For the first time ever in infrared light, astronomers can see it clearly, confirming what radio telescopes have long hinted at. This cosmic engine doesn't just shoot material in one direction, but in two. To appreciate how monumental this discovery is, let's rewind a bit. M87 has fascinated astronomers for centuries. It was first catalogued in the 18th century by the French astronomer Charles Messier, who described it as a fuzzy, starless patch in the night sky. What he couldn't have known is that hidden within that faint glow was one of the most massive black holes ever discovered, a gravitational titan 6.5 billion times the mass of our Sun. This black hole, M87, powers one of the most spectacular phenomena in the universe, a relativistic jet, a stream of plasma launched from the very edge of the black hole's event horizon. It's not the black hole itself that emits the light, but rather the material swirling around it, superheated and ejected at nearly the speed of light by intense magnetic fields. Using Webb's near-infrared camera, or NIRCam, a team led by Jan Roeder of the Institute of Astrophysics of Andalusia in Spain captured this jet in 4 different infrared bands. But it wasn't as simple as pointing the telescope and snapping a photo. M87 is full of stars, dust, and background galaxies that can easily obscure the jet's fine details. So, the researchers painstakingly removed these layers of visual noise, subtracting starlight, filtering out cosmic dust, and isolating only the jet's pure emission. The result? The most detailed infrared portrait of M87's outflow ever assembled. The new image revealed something remarkable. Closer to the black hole, the jet takes on a corkscrew or helical shape, twisting and spiraling outward as if being guided by invisible magnetic forces. Within this region, Webb captured 2 key features that astronomers have long studied. The first is a slower-moving structure known as Knot L, and the second is a brighter, faster region called HST1. HST1 is particularly interesting because of its seemingly superluminal motion, an illusion that makes it appear to move faster than light, caused by its angle and velocity relative to our line of sight. Webb's infrared vision revealed that HST1 actually splits into 2 distinct substructures, each with its own emission characteristics. This means the region isn't uniform. It's a turbulent zone filled with shocks, collisions, and waves of energy rippling outward from the black hole's vicinity. Farther out, Webb detected the faint counterjet, stretching about 6,000 light-years from the core. It appears as 2 thin filaments joined by a glowing hotspot, forming a subtle C-shape that matches what radio telescopes have seen before. But seeing it in infrared light adds a whole new layer of understanding, allowing astronomers to trace how particles within it accelerate, lose energy, and interact with surrounding magnetic fields. So, what exactly is causing all this glowing light? The answer lies in a phenomenon called synchrotron radiation. This is light emitted by charged particles, mostly electrons, as they spiral around magnetic field lines at near light speeds. The radiation spans a wide range of wavelengths, from radio waves to visible light, and now, thanks to JWST, into the infrared. By analyzing subtle differences in color across Webb's infrared bands, the researchers were able to measure how these particles gain and lose energy along the jet. The changes in hue reveal where acceleration peaks, where cooling dominates, and how the jet twists and bends under the influence of magnetic turbulence. This might sound like abstract astrophysics, but it's actually one of the most important frontiers in understanding how galaxies evolve. You see, jets like M87s aren't just spectacular to look at, they play a crucial role in shaping the cosmos. When a black hole fires off a jet, it can inject enormous amounts of energy into its host galaxy and even into intergalactic space. This energy can heat surrounding gas, suppress star formation, and redistribute matter across vast regions. In other words, these jets help regulate the life cycles of galaxies themselves. They act as cosmic feedback systems, ensuring that galaxies don't grow too large too quickly, and spreading elements and energy that may eventually seed future generations of stars and planets. The M87 jet is one of the best laboratories we have to study this process in action. Every knot, every filament, every flicker of light tells us something about how black holes interact with their environments, how they devour, how they eject, and how they shape the universe. And what makes Webb's contribution so extraordinary is that it gives us an entirely new way to see it. While optical telescopes like Hubble can capture visible light and radio telescopes can detect long wavelength emissions, Webb's infrared vision cuts through dust and reveals hidden details that were invisible before. It bridges the gap between what we can see and what we can infer, turning M87's jet from a distant mystery into a detailed, evolving structure we can actually study in depth. Astronomers are now using this data to refine their models of how jets are launched and sustained. The leading theory suggests that the black hole's magnetic field, twisted by the rotation of the accretion disk, acts like a cosmic slingshot, flinging particles outward at near light speeds. But the exact mechanisms are still unclear, and Webb's data could hold the clues needed to finally understand them. It's also worth noting how remarkable it is that Webb was even able to capture the faint counterjet. Because it's moving away from us, its light is redshifted, stretched into longer, dimmer wavelengths that are incredibly difficult to detect. Yet Webb's sensitivity and precision made it possible, giving astronomers a rare opportunity to compare both jets side by side. That comparison could unlock answers to one of astrophysics' biggest questions. Why do some black holes produce enormous, stable jets while others remain quiet? What makes M87's black hole such an efficient cosmic accelerator? And what determines the direction, power, and longevity of its outflows? The answers could reshape how we understand black holes not just as destroyers, but as engines of creation, catalysts that help build the universe as much as they tear it apart. So, as we look at Webb's dazzling new image of M87, we're not just seeing a black hole and its jet. We are witnessing one of nature's most powerful forces in action, a dance of matter, magnetism, and light that stretches across tens of thousands of years and millions of light years. From Messier's first notes in the 1700s, to Hubble's discoveries in the 20th century, to Webb's revelations today, M87 has continually challenged our understanding of the universe. And now, with this latest observation, we are one step closer to unlocking the secrets of how black holes shape the cosmos, not as silent voids, but as active, luminous architects of galaxies themselves. Because in the end, the story of M87 isn't just about a black hole. It's about how something born from gravity's most destructive potential can create beauty, structure, and light that reaches across the universe and across time to tell us who we are and where we come from. And that wraps up today's journey through the heart of M87, where a black hole's power sculpts the cosmos itself. If you enjoyed exploring the universe with us, don't forget to like, share, and subscribe to Spaceverse for more stories that take you beyond the stars. From the first black hole ever photographed to the deepest mysteries revealed by the James Webb Space Telescope, there's always more to uncover out there, and together, we'll keep reaching for the unknown. Until next time, this is Spaceverse signing off, where the universe is never out of reach.